Welcome, my name is Michelle Brasso, and in this session we're looking at modern physics on a tiny budget. Now let's scratch that. Let's make this modern physics on a quantum budget. In this session I'm sharing with you activities that you can do with your students to teach them modern physics using equipment that you likely already have or they are very inexpensive. In this session we'll be looking at relativity, the photoelectric effect, Planck's constant, the Standard Model, and polarization. One of the postulates of the special theory of relativity is that physics can be done in any frame of reference provided it's an inertial frame of reference, and it will follow all of those laws that we've learned in mechanics. The special theory of relativity states that any inertial frame of reference is a good frame of reference for doing physics. There's not one special frame of reference in which the laws of physics hold. So as we've gone through history, we know that we've had this sort of self-centered view of us, humanity, that started with the geocentric model that all of these planets and stars orbit around us. Well, we know that that's not true. And we need to kind of move forward away from geocentrism to heliocentrism in the same way that we move forward from thinking that there's just one correct frame of reference to do physics. This activity will show your students that there's not just one frame of reference in which the laws of physics hold. So to set this up, just put a pool table on a cart. To start, the students would just play pool like normal with the cart stationary. Don't judge. And we see here that we get the expected result that I sunk a ball in this pool table. So with the cart stationary, all of the physics seems to work like normal. Now, what if I were to start moving the cart at a constant speed? We'll see what happens to the billiard balls on this pool table when the cart is moving at a constant speed. There is a small portion of time where the cart is accelerating, and I'll do my best to keep it at a constant speed. So you can see the ball's barely moving. That's only because we're accelerating now. So this is a good demonstration that models if you are on a train or on a plane, as long as that vehicle is moving at a constant velocity, then the law of inertia still holds, and we can use all of our laws of physics. Now for a non-inertial reference frame, that means that the object is accelerating. So what we'd expect to see here are some results in which we would not be able to play a game of pool. So here we go. There's your non-inertial reference frame. You probably already know a lot of static electricity demos that you can use with the Van de Graaff generator. You can shock students, make their hair stand up, you can stack the pie plates and see them fly off. You can also make your own classroom mascot by adding a face and hair to your Van de Graaff generator. We can also demonstrate the photoelectric effect with the Van de Graaff generator. So I will start with my Van de Graaff generator. It is grounded currently, and I have the grounding sphere handy. It will take a little bit of adjustment to get everything just right, but we'll be able to actually hear the photoelectric effect. I'll start by turning on the Van de Graaff, bringing it up to speed. And without any assistance, we're going to find that the grounding sphere discharges the main sphere of the Van de Graaff generator with a pretty consistent frequency. See, I can almost keep time to the frequency that we hear the discharges. Now, in order to hear the photoelectric effect, I'm going to use this UV light and I'm going to shine it on the metal. And what we should experience is that the frequency of the discharging sphere occurs quicker because more electrons are being knocked off the metal. I just have to be careful to not be too close that I discharge the sphere. there is an audible and visual difference in how frequently the large sphere discharges to the grounding sphere, and that's because when we shine the UV light on it, more electrons are being knocked off of the metal and being discharged. So this is a fun way that your students can see and hear the photoelectric effect. An effective analogy for the photoelectric effect utilizes phosphorescent vinyl and LEDs. You'll recognize phosphorescent vinyl as it's used to make glow-in-the-dark decals and decorations. Phosphorescent vinyl only glows when struck by light with enough energy. This is an analogy for the photoelectric effect, in which electrons are only knocked off the metal when light with enough energy shines on the metal. If the energy of the light is too low, the phosphorescent vinyl does not glow, nor would electrons be knocked off the metal. I've placed LEDs of different colors, which correspond to different frequencies and energies, onto the phosphorescent vinyl. When removed, the red LED resulted in no glow on the phosphorescent vinyl. The same was true of the yellow LED. The green LED resulted in a little bit of glow, whereas the high-energy blue LED really made the phosphorescent vinyl glow. Classical electromagnetism wrongly predicted that electrons would be emitted after enough energy was absorbed from the light source. The phosphorescent vinyl shows this analogy as well. Regardless of how long the low-energy red LED is placed on its surface, the phosphorescent vinyl does not glow. The energy emitted was too low to make it glow. Likewise, certain frequencies of the EM spectrum are too low to initiate the photoelectric effect. You can also achieve the same effect with different color lasers instead of the LEDs. This is a great analogy for the photoelectric effect that students can really see. If you're teaching modern physics and your students need to determine Planck's constant, you may be able to do that using spectroscopy. You may be able to do that using a fancy Planck's constant determination apparatus, or, hear me out, you can use Play-Doh and LEDs. For this experiment in determining Planck's constant, you'll need just a few simple materials. A power source, you can also use a battery, your favorite Play-Doh, 2 paper clips, your favorite voltmeter or multimeter, and different color LEDs. The first step is not too difficult. We're going to take out the Play-Doh and we're going to make a Play-Doh snake. The Play-Doh acts like a variable resistor. So the higher voltage you're using, the longer the snake of the Play-Doh has to be. It is conductive, but it's not a great conductor. Once we've got the Play-Doh snake made, we'll want to bring it fairly close together. And on each of the 2 ends, we'll insert a paper clip. The lower the voltage, the less Play-Doh you'll need. So if you go with a higher voltage, you'll need a longer Play-Doh snake here. I'll be using 4.5 volts. I've grabbed a blue LED, and of course the longer leg of the LED is the positive terminal. So I'll just bend those legs and connect it into the Play-Doh. And when I turn this on and up to 4.5 volts, I can see that this LED has lit up. I want to bring the LED to the point where it just barely lights up. In order to do that, I have to bring the LED further away from the paper clips. You can see at this point the LED does not light up. So I'll get in there closely and carefully and bring that LED just to the point where it starts to light up. And I kind of wiggle it a bit forward, a bit backwards, I check very carefully, and I kind of cup my hand here just to make sure that I'm getting the exact right spot where that LED just starts to light up. So this will be better suited in a really dark classroom. If I cup that, I can see that it's not quite on, it's just barely on there. So your students will wiggle it back and forth, moving it a little bit forward, a little bit backwards, until they get to just the perfect spot where that LED starts to shine. That's when our multimeter or voltmeters kick in. Now that we think we've got the LED right at the point where it starts to light up, we'll use our multimeter to find the potential difference across the LED. And students will record that value, and it will go on a graph as well. Students will repeat this with different color LEDs. Here is some sample data from the Planck's constant experiment using LEDs and Play-Doh. First, the students are given this information here, the color and the corresponding wavelength of the LEDs that are used, and they're asked to determine what the frequency is. They can calculate this by hand, or they can do this quite simply using Google Sheets. And just applying this, I always like to show my students how to do this because I find it can save them a lot of time now and in the future. So now we have the frequency in hertz of each of those colors of LED. And then this column here, this would have been what students measured using the multimeter. When they checked where the light just started to light up, this was the potential difference across the leads of the LED. In order to determine the corresponding electrical energy, all we need to do is multiply the electric potential difference by the charge, which in this case would be the elementary charge. And thank you, Google Sheets, for autofilling that. Then from there, we ask the students to plot frequency versus electrical energy. I'll just zoom out a bit here. We like how quickly the spreadsheet software gives us our graph. And in order to quickly get the line of best fit, we'll head over to Customize and Series. And from there, add the trend line. This one is linear. And we'll give this one a label as well using the equation. This is so nice. It's so quick to grab the slope of this line, which is in this case 7.19 times 10 to the negative 34. So that would be our calculated value here for Planck's constant. In order to determine the percentage error, we're going to find the absolute value between this and the accepted value, and then divide that by the accepted value and multiply by 100. And we find here that we get a percentage error of 8.5, which would be really excellent if your students grab that. Of course, the more LEDs we use, the more data we can collect. So if you have the opportunity to bring in some LEDs with different colors, that's excellent. Just make note here that white LEDs cannot be used because there's not an associated wavelength with white light. Here is the standard model using Lego. First, we have our quarks. In the top row, we have the up type, which are up, charm, and top quarks. In the second row, we have the down type, which are down, strange, and bottom quarks. These quarks are aligned in a row based off of their charge. All of the up type quarks have a charge of plus 2/3, and all of the down type quarks have a charge of negative 1/3. You'll notice here that they all have color, and the reason why they have color in this model is because they experience the strong force. Below we have the leptons, which are the electron, the muon, and the tau, and their respective neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. Those do not have color, and in this model, that shows us that they do not experience the strong force. Speaking of the strong force, here are the bosons. We have the gluon, which carries the strong force. We have the photon and the W and Z bosons, as well as the Higgs bosons. I'm not going to focus on that so much right now. Let's just stick to the quarks. A nice hands-on way to incorporate Lego bricks in the standard model is having your students start by making the proton and the neutron. They already know that the proton has a positive 1 charge. So we look at these up and down quarks. What combination gives us an overall charge of +1? And we have this requirement that we use all 3 colors. So how can we do that? We can get a +2/3 and a +2/3 and a -1/3, and that adds up to +1. So a proton is made of 2 up quarks and 1 down quark. How do we make a neutron, which is electrically neutral? Well, we need an up quark of +2/3 and 2 down quarks. When we add those together, it's electrically neutral, and we have a neutron. From there, we can start building some simple atoms. For example, here is a hydrogen atom. We have 2 up quarks, 1 down quark, and an electron. You can challenge your students to making a helium atom. A helium atom is made of 2 protons, 2 neutrons, and 2 electrons. So the students will really enjoy adding all these 12 quarks together and the electrons to model helium. Your students will love using Lego to better understand the standard model. This book has lots of other analogies that you can use to explain the standard model to your students. The polarization of light shows that light is a transverse wave and not a longitudinal wave. I love to include creative activities to support the learning objectives, so here is an artistic application of polarization. To complete this activity, your students will need glossy tape, polarizers, and a transparent surface like old overhead transparencies. These are the 2 brands of tape I've used. Make sure you find clear, glossy tape and not matte tape. Overlap layers of tape at different angles to achieve this effect. Since LCD monitors are already polarized, you can hold the artwork between an LCD monitor and the polarizer. Alternatively, you can place the artwork between 2 polarizers and in front of white light, then rotate either the artwork or one of the polarizers to see different colors. More layers and angles result in a more interesting art piece. What a perfect marriage of science and art. I would love to connect with you. I'm at Mrs. Brassos Binder on Instagram and TPT, or you can email me at mrs.brasso@gmail.com.